Welcome everybody to this lecture on non-target analysis, determining exposures to previously unknown contaminants. My name is Carlton Prasse. I'm an assistant professor in the Department of Environmental Health and Engineering at the Johns Hopkins University. In this section, I'm going to give a bit of an introduction into this approach and the reason why this really has expanded the way we can assess exposures and identify chemicals that we're exposed to in occupational settings and other settings. The main novelty here is really that with non-target analysis, we can look for compounds that have previously not been identified. So basically, we are opening up the lens to compounds that are unknown. And this is in contrast to what is called targeted analytical approaches that we are typically using to detect and quantify known chemicals and for which we typically have reference standards that are available. So you can buy a standard. This allows you to detect these compounds, but also to quantify them. The issue with that is that we typically only look for a small number of chemicals. And again, that's why it's called targeted analysis. We develop these specific methods to look for known chemicals of concern. What is missing here, though, is that in typical settings, we're not exposed to just individual chemicals, or at least in most settings, we are not exposed to individual chemicals, but typically these exposures occur complex mixtures. And these occur chemicals that are used in occupational settings, but it also includes potential transformation products. And I will be talking about this a bit more. What these comprise both metabolites, so compounds that are formed in the human body, as well as compounds that are formed in an occupational setting, for example, as a result of exposures to things like reactive oxygen species or UV light. And this non-target analysis is really linked to the development of very advanced chemical analytical tools, in particular high-resolution mass spectrometers that allow us today to identify the presence of these unknown contaminants. And I want to spend some time briefly on kind of like the definition. So as I mentioned already, when we say target analysis, we typically mean the analysis and also the quantification of a specific known contaminant, and typically with the use of reference standards. And this is typically very hypothesis driven. So for example, we expect a specific contaminant, let's say, for example, a pesticide or a chemical that is used in an industrial process to be present. And so we are specifically looking for this compound. In contrast to this, we are also using the terminology suspect screening. This means that we have an indication of a compound that might be present. So, for example, we know that a whole variety of different chemicals are used in occupational settings. One thing that I will be giving an example of is hair product ingredients that are used, for example, in hair salons. So when we study the exposures in hairdressers, we can basically use this list of suspected chemicals that might be present. So this is really just a list of chemicals that we have in a database that we can then compare our results to. And then last but not least, we have this what is called non-target analysis, or also called NTA, which basically means that we are characterizing chemicals that are present in a sample without any previous knowledge regarding the chemical content of the sample. So we basically are completely blinded to what might be in the sample. We're letting the analytical tool identify which compounds are in there. And one way how I like to envision this is kind of thinking about when you walk down a street at night and you have different lamps along the way. The lamps typically only light up the area right underneath the lamppost, which is how I like to think about the target analysis part. In contrast to this, when you think about non-target analysis, you can think about a stadium floodlight where you just light up the entire street, basically. And so this is kind of like visualizing a bit how non-target analysis differs from target analysis. And then on the other side, when we think about suspect screening, as I mentioned, this is typically where we look for compounds that might be expected to be present, for example, in occupational environments. And one way of doing this is you can, for example, use questionnaires or safety data sheets to assess all the products that are being used. So as I said, this can be, for example, hair products that are being used in a hair salon, or all the chemicals that are used in a chemical production facility, for example. This can also comprise the use of inventories of chemicals that are used. So for example, again, products used in hair or nail salons. So through, for example, material safety data sheets, which is very common, for example, in laboratory settings. And then last but not least, and this is something that only has become available more recently, is the use of chemical online databases, such as ChemSpider and the ComTox dashboard, which are online databases that are compilations of large amounts, in most cases over millions of chemicals that are categorized into different lists. So for example, dyes or cosmetic ingredients or personal care products or pharmaceuticals. When we think about a non-target analysis, the main challenge is that non-target analysis, or NTA, relies on the use of chemicals or detection of chemicals that are often not included in any databases. And as I mentioned before, when we apply non-target analysis, we analyze samples without actually knowing what's in the samples. And one aspect that is important to think about is kind of like the chemical space that different approaches can detect. And this is kind of like highlighted here. So on the left side of this graph, you can see in these three different circles, the chemical space. So this is basically the chemicals that are present in the samples are divided into what is called knowns. So this is like the smallest circle here in orange, which are the chemicals that we know are present. Then the known unknowns, these are chemicals that we think they are present. So for example, based on the suspect screening list. And then there are these unknown unknowns, which are chemicals that we have no previous knowledge about. And this translates to the different analytical approaches, which is shown here on the right side, with the target analysis targeting the knowns, the suspect screening targeting the known unknowns, and non-target analysis targeting the unknown unknowns. With the size of these circles, what is also indicated is that the chemical space that these different approaches are able to cover. And again, one of the main advantages of especially non-target analysis is that it really allows for the identification or the detection of previously unknown exposures, which is a big advantage compared to the target analysis strategies that we have used primarily in the past. The technology that we are relying on for these non-target analysis and suspect analysis approaches is, as I mentioned before, high-resolution mass spectrometry. And the reason why these have only become available more recently is that the development of this instrumentation has really only been developed over the last 1 or 2 decades. And what these high-resolution mass spectrometers allow us to do is simply they measure the masses of organic compounds, or more specifically their ions, with a very high accuracy. And based on the detected masses, and this is the advantage of this technology, we can then determine the molecular formula of the detected compounds. So we can basically say what the molecular composition is. So for example, how many carbons are in the molecule, how many oxygens, how many hydrogens. In addition to the detection of these, what we call parent masses, or the original masses of the molecules, we can also fragment the ions that are coming in. These are so-called MS2 spectra. And the advantage of fragmenting these molecules is that the individual fragments that are forming are also providing us additional information on the chemical structure of the detected compounds. So to just give one example, if a compound, for example, contains a carboxylic acid group, we see typically a cleavage of 44 or 46 in negative or positive electrospray ionization. So this is just one example how these fragments then can also help to get additional information of how this molecule actually looks like. Another aspect that I want to point out is that these high-resolution mass spectrometers are typically coupled to either gas chromatography or liquid chromatography systems, which allow to separate individual compounds that are present in the sample. Because as I mentioned earlier, typically when we analyze either environmental samples or biospecimens such as blood and urine, we are typically not dealing with just the detection of a few chemicals, but typically we detect hundreds or even thousands of chemicals. So having this chromatography system that basically separates out the individual compounds is another important strategy to ultimately detecting these compounds. To emphasize this aspect of importance of high-resolution mass spectrometry a bit more, I just want to give an example here. So what you can see here are 2 different compounds, dimethyl phthalate, which some of you might have heard. This is a plasticizer that is used in plastics. And then butylparaben, which is a preservative that is frequently used in, for example, personal care products. And when you look at the monoisotopic mass, which is basically the mass of the molecule, you can see that they are relatively similar. And if you would use a low-resolution instrument, they basically would look the same way. So low-resolution instruments mean that they can basically just detect, okay, is this a 194 or a 195? So in this case, for both compounds, they would look basically identical. But what high-resolution mass spectrometry allows is really, it gives us the accuracy to measure these masses with up to 5 digits, which is basically shown here. And again, as I mentioned earlier, using this monoisotopic mass of the molecule, we can determine then the molecular formula, which is shown here in the middle line, basically. And what you can obviously also tell already from the chemical structure is that both of these chemicals are not the same. They look very different when you just look at it visually, but they also, when you look at the molecular formula, they also have a different molecular composition. And being able to distinguish these two, you can imagine, is very important from the perspective, for example, of if you want to assess the risks. So if you know exactly what you're looking for, you can then think about, okay, what is the potential toxicity? It's very likely that the toxicity of both of these compounds is very different. So knowing really or being able to distinguish between them is a very important aspect. Now, as I said before, non-target analysis is an extremely powerful tool, and typically we can detect hundreds or thousands of different what are called features in a single sample. So I want to briefly talk about what features are. So features represent unknown compounds that are generally described in terms of their monoisotopic masses, their retention times, and their isotope distribution. And so what this means is that typically you have several features that make up a single compound. The main challenges with these large numbers of features or compounds that are present in samples to figure out, okay, which ones are the ones that are actually of relevance. And this is highly dependent on the goal of the study that you are intending to do. And so, for example, the question is, are you interested in assessing, for example, the presence of contaminants in different environmental media that you're exposed to? So thinking about, for example, air or water. Or are you interested in monitoring, for example, exposures in an occupational group of people by monitoring, for example, the blood and urine? And one aspect that I want to highlight here is that especially when we look for the biospecimens, so if you take blood or urine samples from different individuals, one thing you have to think about or take into account is that some chemicals, once they are ingested in the body, they are metabolized. And so if you want to assess exposures, you typically also have to take these metabolites into account. Because we know for some chemicals that they are very extensively metabolized, so you wouldn't actually be able to detect them, but you might be able to detect the metabolites. And to just differentiate that, you can think about this again from kind of like monitoring outside and inside the body. So when we think about external chemical exposures, we are thinking about chemical contaminants, for example, that we're exposed to, or also environmental pollutants. So what I mean here is more like the chemical contaminants are very specific chemicals that are used, whereas when I talk about environmental pollutants, these are more like dispersed chemicals that, for example, might not be directly used in an industrial process. We also have to think about lifestyle factors. So for example, just smoking. So if you want to monitor occupational exposures, you typically also want to monitor for or account for other factors such as smoking that might contribute contaminants or exposures to contaminants. Then again, it heavily depends also on the occupation, both in the sense of what chemicals are you exposed to, and again, what is your reference? And then last but not least, diet also can play an important role in terms of chemical exposures. So these are all what we call external chemical exposures. And this is in contrast to then biomonitoring, where we basically go inside the body and monitor, for example, or take, for example, blood or urine samples, where we are looking for in these matrices for both chemical compounds and their biotransformation products. For some chemicals, we can also use DNA and protein adducts. So this is important for chemicals that react, for example, with DNA and proteins. So in this case, we might not necessarily detect the original compounds, but we can use these so-called adducts to detect exposures. And then another aspect that is also interesting or important from a public health perspective is to think about what are potential perturbations that are resulting from chemical exposures. So for example, do we see differences in natural metabolites that our body forms, or difference in lipids or hormones? So this can also give further information about potential health effects that are resulting from chemical exposures. And in addition to these metabolites that I referred to earlier, one aspect that is also important when we think about chemical exposures is that also the environment that we are in can result in the transformation of chemicals and the formation of these so-called transformation products. So for example, when we think about disinfection strategies that are used, for example, in hospitals or in other settings where we, for example, use chlorine, which is basically bleach, Or if we are in indoor environments, we are typically also exposed to reactive oxygen species, ozone and hydroxy radicals, which can react, for example, with different contaminants and form these transformation products. UV irradiation is another important aspect, which is used for both disinfection, but also in some technical industrial processes. And irradiation can also lead to a degradation of organic chemicals. And again, if we're thinking about monitoring for exposures, we also have to think about what do these reactions lead to, and are there any byproducts that we want to also assess. And similar to this, we also have to think about other technical processes that use, for example, ionizing radiation, oxidizing chemicals, or also plasmas that are sometimes used. And the main reason why it is important to account for these transformation products is that there are numerous examples that have shown that some of these transformation products can actually be more problematic than the original compounds that they originate from. So again, if we really want to do an exposure assessment and think about what are potential health implications of these exposures, it is very important to also think about these transformation products. And just to give you a few examples, so for example, disinfection of surfaces, as I mentioned earlier, which is very commonly used in, for example, in hospital settings. If you use bleach and you, for example, disinfect plastic surfaces that, for example, contain bisphenol A, BPA. A lot of you might have probably heard of bisphenol A. When you buy today plastic bottles, it often says free of bisphenol A. But just as a side note, it doesn't mean that they don't use any chemicals, they just use different chemicals. But if you basically have a surface that has bisphenol A on it and you add bleach to it, what basically happens is what is shown here, that this bisphenol A reacts with chlorine and forms these different chlorinated species that are indicated here. And what we know is that typically, if you add chlorine to an organic compound, you typically increase the toxicity. And it actually, for these compounds, it has been shown indeed that there are different toxicities that are resulting from this process in which bisphenol A reacts with chlorine. At the same time, if you use, for example, UV irradiation, which is also in certain settings used as a disinfectant, in this case, for example, using UV light at a wavelength of 254 nanometer, which is also abbreviated as UV 254. This bisphenol A is basically degraded by the UV irradiation and forms these three chemicals that are indicated here on the right side, such as phenol, hydroquinone, and benzoquinone, some of which are also toxic. And again, that's why we are interested in also thinking about these transformation products. In addition to these transformation products, the metabolism, also to give an example here, organic chemicals, if we are ingesting them or if we're exposed to them via air or food or through the skin, a lot of them are substantially metabolized, especially in our liver. We typically categorize this metabolism into two different phases, where we call the first phase, or phase one, which is the oxidation, which is the most common reaction. Sometimes for some compounds also reduction or hydrolysis reactions can occur. And this is separated from what is called phase two, where you have a conjugation reaction, where you basically add a molecule to your chemical, such as glucuronidation or sulfation, which the body basically does to increase the polarity and help basically the excretion of this compound via urine. So the goal of our body of doing these reactions is basically to make it a compound more polar so that it can be excreted more easily. The issue here is that in addition to the fact that if we want to assess exposures, we need to account for these metabolites, the metabolism is also important to consider because it can lead to the formation of toxic metabolites, which we call bioactivation. And I'm just giving one example here to illustrate this. So polycyclic aromatic hydrocarbons, or short PAHs, which are ubiquitous chemicals, so we are surrounded by them, I think, all the time. They're originating from things like combustion processes. So for example, when you think about cars, when you think about wood fire, when you think about coal fire combustion plants. So these are present in our environment. And when we inhale them, for example, or expose to them via other pathways, what happens in our liver is that by different enzymes, in this case, I'm illustrating here cytochrome P450, which are enzymes that are very prevalent in our liver, you form these different metabolites that ultimately lead to epoxides that are very toxic because they can, for example, react with our DNA and then result in toxicity in the people that are exposed to them. Another example that I like to give is the metabolism of acetaminophen or Tylenol. Might be more commonly known when you go to a pharmacy, for example. So what happens with acetaminophen, similar in the liver, is that also here by cytochrome P450, you're forming this intermediate compound that is shown here in the middle that is reacting with proteins in the liver and thus can cause liver toxicity. Maybe a little fun fact, this is the reason why you shouldn't take acetaminophen after you had a couple of drinks the night before. The main reason is that by the consumption of alcohol, your body produces more of these cytochrome P450 enzymes. And so what happens then if you take acetaminophen, you actually form more of this toxic metabolite. And again, just to highlight that the metabolism is very important to consider both from the perspective of exposure assessment, but also when we think about the toxicity of different compounds.